Okay. Hello, everyone. Welcome back. This is CP 517-WS Digital and Computer System Architecture course, Lecture 2, Part 4, Other Performance Matrices than what we discussed before. Your Professor Hang Liu here. So the performance of a computer, no matter you are from computer science or computer engineering, right? So I bet you must have this kind of answers from your parents or from your friends. They just ask you, hey, can you help me purchase the fastest computer or best computer for me? So how could you answer this question? You shouldn't directly go say, hey, this is the best CPU, this is the best memory, this is the best NIC or GPU. You should ask them, what is your workload, right? So if your friend is good at gaming or pay a lot of attention to gaming, excuse me, so maybe GPU is important, and you should run some gaming or multimedia benchmarks in order to test which computer is better. If your friend is doing something for financial banking or other things, probably mathematics, CPU is better, or Microsoft benchmark is good, right? Like Office. So basically, we're trying to say, okay, you want to understand what is the workload, and you want to have the correct measurement and analysis, which we're going to talk about later. And you also want to understand that how much your customer or your friends want to pay, right? Cost is also very important criteria. So the other matrices are MIPS, million instructions per second, or MFLOPS, million floating point operations per second. MIPS equals the instruction count divided by execution time, multiplied 10 to 6, because it's a million instructions per second, right? So it equals clock reads divided by CPI, okay? Well, we want to also be clear that MIPS has serious shortcomings. Why? It ignores the program. You only use to quote peak performance with ideal conditions, but MIPS can be a problem, for example, if you use different compilers or different instruction set architecture. Because MIPS assumes you have the same clock cycle and same number of instructions, right? So that means same number of instruction means the same compiler, same instruction set, and same clock cycle means you have to run the same instruction set architecture. Otherwise, let's say if you run one instruction on Pentium 3 and the other on Pentium 4, maybe your MIPS is lower on instruction Pentium 4, but actually faster, because you might have fewer number of instructions and maybe other things, right? We don't know. So we want an instruction count per program to be constant and it can be ignored. That's the case, right? You can see here, you have this instruction count divided by execution time. And then if you have the same number of instruction count, then definitely higher MIPS is better. And then you want to have the same cycle. That's why we see instruction count per program should be constant. Right? Other matrices like million floating operations per second, this is what's very important. It's typically used for high performance computing. Assuming floating point operation is independent of compiler and instruction set architecture, it's often safe for numerical codes, like matrix size determines the number of floating point operations per second, no matter what kind of compilers they're using or like instruction set you are using, because the floating point operation is associated with the problem. However, it's not always safe, because for some compilers, you might miss some floating point division or special function units like sine, cosine. So, and also there are optimized compilers that can reuse the results of before, which I also did a couple of those kind of optimizations before. So M flops can also be problematic, right? Relative MIPS and normalized M flops, normalized to some common baseline machine like VAX MIPS in the 1980s. So typically people only refer to time, okay? We only use time. So if you have shorter time, you're faster. I mean, that's very fair. And also you want to be sure that you don't focus only on peak, because peak is not always achievable. Okay, so with that in mind, can you use 15 to 20 minutes to solve this problem, right? Okay, and I'm gonna post the results later.